We're going to start by looking at a review of the Lewis structure modeling from the last chapter because it does come into play again in the current chapter. We want to start by looking at how many electrons each element contributes to the structure. So for example, hydrogen is in column 1. Each hydrogen contributes 1 electron, and there are 2 hydrogen in this formula. So therefore, that's a total of 2 electrons just from hydrogen. Oxygen is in column 6, so it contributes a total of 6 electrons to the structure. So that gives us a total of 8 electrons that need to be distributed. So our Lewis structure puts oxygen in the middle and then hydrogen on the outside. We used 4 electrons, 2 from each bond, to bond the elements together. So subtracting 4 from the total gives us 4 that still need to be distributed. So remember, hydrogen already has its duet filled, so that means we put 2 more lone pairs on oxygen. This gives us our total of 8. Oxygen has its octet. Each hydrogen is following the duet rule. Our electron domain geometry, since we have 4 domains, is tetrahedral. Molecular geometry is going to be just a little bit different because we do have the non-bonded pairs. So a tetrahedral electron domain geometry with 2 non-bonding or lone pairs gives us a bent geometry. What that bent geometry is going to do is these electrons are going to push these other ones down just a little bit. And when we do this, we create now a structure where we have a partially negative charge up at the top and a partially positive charge down at the bottom. This means we do have a polar structure. Now looking at our next molecule, so this is propane. Again, we need to count up the valence electrons. Remember, carbon has 4 each times 3. This gives us a total of 12. And we're going to add to that each hydrogen contributing 1 times 8. So 12 plus 8 gives us a total of 20 that need to be distributed. So remember, hydrogen can only go around the outside, so we're going to start by putting carbon in the middle, all 3 carbon in the middle, and then hydrogen all around the outside. Notice we have included all 8 hydrogens, and then if we count up the bonds, we get 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So we've distributed all 20 electrons here. The carbons have their octet satisfied and each hydrogen has its duet satisfied, so we're good to go with this Lewis structure. For our electron domain geometry, we're looking at the central carbon atom. So just the one in the center that has a carbon on each side and a hydrogen on top and the bottom. So our electron domain geometry is going to be based on the number of domains here. So remember, a domain is either a single bond, a double bond, a triple bond, or a lone pair. So here we've got 4 single bonds, so this is a tetrahedral electron domain geometry. The molecular geometry only changes when we have any lone pairs here, and since we don't have any, our molecular geometry is going to be the same. Now, we are looking at the polarity of this molecule. I cannot put a plane anywhere through this molecule that would separate any sort of positive or negative charge. If we go back to the main Lewis structure, we can see that essentially what we have is one charge within the center surrounded by all of the same charge around the outside. So this is what we would call a nonpolar molecule. In the first section of this chapter, what we're looking at is 2 different things. 1, to understand the process of dissolving, and 2, to learn why certain compounds dissolve in water. So we do this a lot when we look at salt in water or sugar in water. We see that it's dissolved, but we don't really understand what's happening during the dissolving process. And then some things dissolve in water and some don't. And that's the second thing we're going to look at, is why do some things dissolve and others do not. So when we're looking at dissolving, remember NaCl is an ionic compound. It's made of a cation and an anion. So we're talking about those electrostatic interactions, those ionic forces that hold the compound together. So the reason that salt dissolves in water, by nature it's a polar compound, so it's got a positive end and a negative end. So what's going to happen, as soon as we start putting this salt in water, the water is then going to orient itself in a way that will surround those salt ions, the sodium ions and the chloride ions, and then it will pull them apart from each other. There are so many of these water molecules that it's very easy for them to surround each of the individual sodium or chloride ions. So what we see happening is that the water surrounds atoms in order to separate them and break apart the salt crystal. In order for that to happen, the water has to turn itself around one way or another. Notice in this particular water molecule right here, we've got that red end, the negative end at the top, and we've got the positive hydrogen end down at the bottom. This particular situation is set up so that the positive end of the water molecule, again looking at it this way, we see that it looks something like this. This being our positive end, this being our negative end. So we see that the positive end of the water molecule has oriented itself in a way that it is making contact with the negative end of the salt ion, the salt crystal, the chloride ion in the salt crystal. And we see in this other situation down at the bottom, we have the opposite happening. This molecule is now flipped to where we have hydrogen at the top and oxygen down at the bottom. So here we end up with our positive end, and down here we end up with our negative end. And that's what we see happening right here. We have the positive end at the top, we have the negative end at the bottom making contact with that positive sodium ion. So the attraction between the water molecules and the ions is stronger than those ionic attractions are to each other. It's easier for them to pull it apart than it is for the salt and chloride ion, or the sodium and chloride ion, to stick together. Just a closer look at what we've been seeing happening here. This is our positive end. This is our negative end. Positive and negative. And again, notice what's happening. Sodium is positive, so positive and negative are attracted. Chlorine is negative, and again, positive and negative are attracted. When we have an ionic salt, now salt in our case does not necessarily mean table salt, it means any ionic compound. So when we have a salt and we dissolve that salt in water, we end up with what's called an electrolyte. And we've heard of these things in Gatorade or Powerade or any of those drinks that claim to have electrolytes. So electrolytes just refer to the fact that they have a current flowing through them. So when we see something like NaCl, and when we dissolve that NaCl in water, we have what's called dissociation. Dissociation just means breaking apart. So we get sodium ions and chloride ions. So the positive and the negative charge, when this is all put together in what we would call an electrolytic cell, forms a battery. And the idea here is that one of these is going to flow towards the anode and one is going to flow towards the cathode, and the movement of this charge is what makes it possible for electric current to flow. The fact that these charges are present in a solution is what allows electric current to flow and electricity to move through a solution. Knowing the polarity of a compound allows us to figure out what will dissolve in water and what won't. So you can see this line going through the center here, looking at an example of something like oil and water, gives us an interface where the two meet. So down on the bottom, we see this one, for example, is like a regular water molecule. It's a hydrogen, oxygen, and a hydrogen. We've got the positive charge here and the negative charge here. That positive end of a polar water molecule is going to interact with what would be negative around the outside of some sort of oil. So this is where we have a non-polar-polar interface. So this is why things like oil and water don't mix. Oil is going to be essentially a positive charge around the inside surrounded by a negative charge on the outside, and then that is going to have an interface with a water molecule. Because this negative end of the water molecule can't interact with anything on the surface of the oil, they won't come into contact with each other. They will keep each other at a distance and not mix. So this is why we say like dissolves like, polar compounds can dissolve other polar compounds because they can fit in the middle of these negatively charged ends of the water molecule. Whereas in a oil or fat molecule, we don't see that happening. We have just negative around the outside, which means this negative won't find its way in to be in between those negatives, because we know like charges repel. So like polarities can dissolve one another because they would both have a positive and a negative end. But if I'm talking about something that is a nonpolar molecule, it is all surrounded by the same charge, which would be the same as one end of a polar water molecule, but not both. So the samples can't mix.